Today we're going to be talking about the continuity of a function, or rather, whether a function is continuous. What you will notice throughout is when we're talking about this, it does not necessarily mean that a function in its entirety is continuous, that it is one solid piece, but rather that within a particular area or domain we are looking at, it is continuous, or one piece, or one continuous function. And so you'll notice that this label or this title of this lesson today is about continuity or continuous function at a point. When we're looking at this, we are looking at specific points or specific domains in which we're examining in that particular area, is it continuous? Now, to be continuous, that must mean then that the limits from each direction and the value at that point must agree. Let me say that again. To be continuous, then the limits from each direction, positive, negative, right, left, and value at that point must agree. Now, looking at the graph you see in front of you, what this is basically saying is that this graph, okay, is not continuous at x equals 2. But it is continuous everywhere else. And hopefully that seems obvious to you. In a very simplified version of this, in essence what's happening is, as we come from the left-hand side, we see, oh, we're continuous, we're continuous. We get to 2, and we have to pick up our pen in order to continue on with the function. And there, right there, as simplified as I can make it, if you have to pick up the pen at any point, it is not continuous as a function. But again, if I was to say, is this function continuous as x is greater than 2? And you would say yes. Is the function continuous at x is less than 2? And of course, yes. So let's examine this for a moment to illustrate what I'm talking about here. To be continuous, then the limits from each direction and value at that point must agree. If you were to look at this graph again, 2 plus, that means I look at 2 and I'm looking just to the right. So here we can see that the limit, as I'm approaching from the right-hand side, is actually approaching the value of 3. 2 negative, or from the left, as I'm approaching, it's approaching 1. The value at 2 is where this solid dot is, it's back to 3. Now, even though 2 of the 3 agree, it does not matter. That means that the limit as x approaches 2 does not exist, and therefore it is not continuous at x equals 2. All right, let's look at another example here, 1 plus. If I now erase my red here so that's not too confusing, and we find 1. Well, here's where 1 would be. 1 to the right, oh, it's approaching 0. 1 from the left, okay, it's approaching 0. And the value at 1 is 0. Since these all agree, that means the limit as x approaches 1 is in fact 0. That's exactly what the answer is. All right, let's look at another example here. Within this graph, 3 plus. Again, we're going to look at 3. We'll look just to the right of that. All right, it's approaching 2. 3 minus, so that means to the left. Okay, it also is approaching 2. But the value at 3, let's just say that that's 1. Since they do not agree, then the limit as x approaches 3 does not exist. And in fact, demonstrates that it is not continuous at x equals 3. Okay, graphically speaking, what we're looking at is it one piece or not? It's as simple as that. Analytically, mathematically, what we're looking at is the limit from the right, the limit from the left, and the value at that point is exactly the same. They are all equal. And that tells me that it is, in fact, continuous. Now we're going to change gears from here. Hopefully you understand at this point what continuity means and what continuous at a point means. And we're going to look at another avenue. I want to remind you of a few things because you're going to see some questions like this on your homework and in class tomorrow. And so I just kind of want to remind you specifically about e to the x and even our natural log function a little bit. So before I go too far, let's just look at the e to the x graph. Hopefully we remember this. The e to the x graph, if you recall, kind of starts near the x-axis and then swoops up. Does anybody remember where it crosses that y-axis? Hopefully there's a resounding one while you're staring at that computer. And so when I ask you e to the infinity, what I'm really saying is e and as far to the right as possible, right? That's what I'm looking at here. And so e to the infinity, do you all follow that that is going to infinity? However, negative infinity, it's not like it's going down. It's getting very, very close to 0. In fact, the way we write that is not just 0, but 0 plus. Good, because it's just a very, very small positive number, and that's what that's representing. All right, now let's look at natural log. Natural log graph, remember, is the inverse of e to the x. And so it runs along the y, and then it starts to bow out there. It also crosses at 1. Now, as the natural log of infinity, that means what is this graph doing on the right-hand side? Although it seems quite misleading as you look at it, because you think, oh, it's going so slow and like it should be rounding to a number. The fact is, it's going to keep climbing. It just takes a very long time. We mentioned last year about how natural log just tends to be like the weakest of functions because of how slow and how, long it takes for it to actually approach infinity. 0 plus, that again, looking at 0, 0 plus would be just to the right. It is going down to negative infinity. Now with those things in mind, let's now answer these questions. We have the limit as x approaches 0 plus of e to the 1 over x. So before I go too far, we're really looking at the limit as x approaches 0 plus e, and we're really putting 0 plus in here. And of course, 1 over 0 plus is the same thing as e to the infinity, and so this is a fancy way of asking you this very question here. All right, let's try this one. So now I have the limit as x approaches 1 plus, and so I have e to the 1 over 1 minus 1 plus. Again, the question is when you're dealing with limits is we understand that this is e and we have 1 over 0, but is that a 0 plus or is that a 0 minus? And so which one is bigger is what we're weighing out. And of course, the 1 plus is the one that's bigger, and it is negative. Therefore, this would be 0, sorry, not negative 0, but 0 on the minus side, which makes this negative infinity. So I'm really looking at e to the negative infinity. Again, this is a same way of asking the second illustration here, just a fancy way of doing so, and so we understand the 0 plus answer there. Okay, we have the natural log of 1 over x squared. And again, we're going to put 0 in there. You'll notice that doesn't say 0 plus or 0 minus. Now, hopefully, we remember that 0 plus, when I square it, would become 0 plus still. It would be still a very small positive number. 0 minus, when I square it, would also be 0 plus, because when we square something that's negative, it would become positive. And so, really, we didn't need to have 0 plus or 0 minus, although it's important that you take a moment to look at that. And so just for all intents and purposes, I'm going to just put 1 over 0 plus, since they both become that very small positive number, making this the natural log of infinity. Again, a fancy way of asking that third question that we looked at already. And last but not least, we have the natural log, and we have 1 minus e to the 0 minus. So before we can go too far, we might want to think about what is happening in 0 minus, e to the 0. But we understand that that really is saying 1 minus 1, right? But which one are we looking at here? We follow, or at least I hope you do. I hope you follow the fact that this is a very small number. And that this e to the 0 on the minus side is small. It's smaller, okay? It's a smaller 1, rather, than this one. And so this would be the natural log, again, of 0. We get that at 0, and it'd be 0 plus. And so for the same reasoning as you've seen, it would be negative infinity. Well, hopefully that gives you some clarification for the questions that you're going to see tonight, as well as the continuity at a point.